All right, this is number 6 from the 2013 AP Physics B exam. This is primarily an EM problem, and we have got two long straight wires. The top wire is 65 amp current flowing through it. The bottom wire is 0.025 meters away from it. It too has current flowing through it, and it has a mass per unit length given. And we know that it is we know that it is below the wire X. And we want to know the magnetic field produced by wire X at the position of wire Y. So that's a simple straightforward one, meaning pretend Y isn't even there. What's the value of the magnetic field 0.025 meters away from wire X? For that, you got to recognize the equation. Magnetic field is mu naught times the current all over 2 pi r, r being the distance away. I being the current, and mu naught and 2 pi are both constants. Mu naught is a constant provided for you, 4 pi times 10 to the negative 7. The current is 65 amps. 2 pi is in 3.14, not radians. And then 0.025 meters is the distance away. And you're going to get 5.2 times 10 to the negative 4 Tesla. That is simply the magnetic field at that location. B wants us to now determine, let me clean this up a little bit. B wants us to now determine the magnitude of the current in wire Y. Now, let's read this a little bit more carefully. Wire Y, which is part of a second circuit, so we know current's flowing through it, is free to move vertically and is suspended at rest by the magnetic force between the wires. So let's think about our dynamics here. Wire Y has weight. It wants to fall down just like any other thing on our planet, but it's at rest, which means there's got to be a force up that's equal to that weight. And that force is the force that comes from the magnetic field. The two wires both have a magnetic field. They're going to act like magnets, and they're going to be attracted towards each other. Therefore, for step B, B1 at least, we know that the magnetic force must equal the weight of the second wire. We want to know the current and magnitude of wire Y. Now, that wire, based on its current being exposed to the magnetic field, must equal the weight. So the force of the wire acting on wire Y is B I L times proper orientation, but it is arranged properly. That must then equal the weight of the wire. Ultimately, we're looking for current, so current is going to be equal to mg over BL. Now let's look at what we've got. We know G, we know B. B is what we found already. M and L we don't know directly, but if we read this carefully, we're going to see it's the mass per length of the wire. So this M over L is this 5.6 by 10 to the negative 3 kilograms per meter. So I'm going to rearrange this, not rearrange it, but slightly change the way it looks. So you can see this part is that number given. Thus, the current is going to be 5.6 by 10 to the negative 3 kilograms per meter times 10 meters per second squared. You can use 981 or 10. We're going to divide that by the value of 5.2 times 10 to the negative 4 Tesla. Let me go ahead and calculate. We're going to get approximately 108 amps. B2, we now know that we need to indicate the direction of the current in wire Y. Well, you don't need to justify, so as long as you remember the rule, when the current and two wires are in the same direction, they're attractive, parallel. When they're in opposite direction, they're repulsive, anti-parallel. Since this guy must be getting pulled up, it's got to be attractive, which means its current needs to be the same direction. So the answer is to the right. All right, part C. Actually, let me go ahead and clean up all my workspace here so it's a little bit easier to show you everything. Part C says that the wire is now moved into a new position. We're going to take wire Y, bring it closer to wire X, but not past wire X, so it's still below wire X. We're going to release it from rest. We want to describe its initial motion, just the initial motion. Well, if it's closer to the wire, it's no longer going to be in equilibrium because the force is going to be larger, because that force relies on the magnetic field, which is going to be greater, because the distance away is smaller. It's inversely related. Since the force is larger, it's not going to be in equilibrium because it's going to be greater than the weight, which means it's going to experience a net force towards wire X, which means it will accelerate. I think the most appropriate answer is to say wire Y will accelerate towards wire X because the magnetic force due to the magnetic field is larger because wire Y is closer to wire X. D. Suppose wire Y is moved to a position 0.025 meters above wire X. What changes, if any, must occur to maintain equilibrium? Well, think about this. Before wire X and wire Y needed to be in the same direction so they'd attract each other. Wire Y needed a force to help pull it up to counteract gravity. Well, wire Y is now up here. That gravitational force is still down, but if they were attractive, then the force of the magnet would be down as well, and it would not be in equilibrium. So wire Y now needs to be repelled away from wire X, and in order for them to repel, they need to be anti-parallel. So wire Y, which is now the above wire, this blue one, must have its current going to the left. Again, you don't need to justify it, but that is the justification in case in a future problem you did need to. E. Wire Y is still above wire X. The circuit is connected to wire Y, or the circuit that was connected is removed. So there's no more current flowing through wire Y. It's simply a piece of metal here. However, now this piece of metal, which is 1.2 meters long, is moved up at a constant speed of 3 meters per second. And we want to know the magnitude of the induced EMF in wire Y when the wires are a certain distance apart. So because this wire is in a magnetic field and it's moving away, it's experiencing a changing magnetic flux which will induce current. There's a core equation that you can eventually derive, or there's the one that you're encouraged to also remember alongside it, and it's the moving conducting rod equation, BLV. So in this problem, when we're looking for the EMF, we're just going to plug in for B, L, and V. We already know, well, actually I'm going to come back to B. We don't necessarily know the magnetic field yet. The length we know, that is the length of the rod exposed to that field, 1.2 meters. The velocity we know. So my question is, what is the magnetic field? Is the magnetic field 5.2 times 10 to the negative 4? Well, it's only going to be that if it's still 0.025 meters away. It doesn't look like it is. It's 0.05 meters away. And if we look at this V equals mu naught I over 2 pi r bit, the I of the bottom wire is still the same. It's the distance away from it that changed. We went further away. It's inversely related, which means the magnetic field will weaken. It's a linear relationship, not exponential, which means if the distance doubles, my magnetic field is half. So instead of using 5.2 times 10 to the negative 4, I'm going to use half of that, or what's half of 5.2? 2.6 times 10 to the negative 4 Tesla times my 1.2 meters times my 3 meters per second. Get that all in your calculator, and you're going to get 9.4 times 10 to the negative 4, and it's EMF. It's an induced electromotive force, so it's going to be volts. Right, that's E1. Now E2, indicate which end of the wire is at a higher electric potential, and then we need to justify. So we know that there is a voltage difference between one end of the wire and the other of 9 times 10 to the 4 volts. So one end is positive, one end is negative. And for this we need to use our right-hand rules, or there's multiple right-hand rules. I'm going to suggest to use the one that is the force acting on a moving charge. So for that, we need to know the external magnetic field. The magnetic field due to this bottom wire above it needs to be coming out of the page. You're going to use right-hand rule number 1 for that. You're going to point your thumb along the direction of the wire, and then you're going to wrap the rest of your fingers around that wire. And above that wire, those fingers would be pointing at you, so that means the field is out of the page. We'll represent that with dots. Alright, I'm not going to draw a ton of dots, just we have dots out of the page. We know the force acting on this wire, where am I at here? We know that, not the force, the movement of the wire is up. And so we need to now know what is the direction of the force acting on the wire. So if we use right hand rule number 2, I like to refer to my index finger as the direction of motion. I like to refer to my remaining fingers as the direction of the field, and that means my thumb is to the right. That means that electrons will be experiencing a force to the right. That must mean the right end is positive, and this end is negative. Another explanation that might help you is thinking about the Lenz's law rules, the Lenz's law right-hand rule, and understand that this conducting wire is moving away from the field, so it's experiencing a decreasing magnetic flux. As a result, it needs to create its own field such that it's in the original direction of the field because it doesn't like that change. And so then you would use right-hand rule number 1 on that. The field created by that wire needs to point out of the page because it needs to be the same direction. And you would wrap your fingers in the direction of current flowing through that wire, and your fingers would, you'd have your thumb this way and your fingers would be wrapping like that. Thus that means current must be going around this wire if it had that loop still, which it has, it's just not a part of the circuit anymore. Thus current must be traveling to the left. If current is traveling to the left, then the high potential is to the right because it goes positive to negative. Alright, that is it for number 6 for the 2013 AP Physics exam.